Hello, hello, hello again, everybody. Welcome back. Today we're doing section 3.2, and this section is all about factoring quadratic polynomials. So you could think of this as like the factoring section. You might have studied factoring quadratics a lot in a previous math class. We're going to do it today. There's a lot of different ways to do it. It is an important skill that you're going to need. And I'll give you some motivation for why we even care about having to do it. All right. Let me get the slides up and we will get started. Okay, here we go. So here's the overview for the section. We're going to review the difference between factors and terms again. That's a critical thing to understand. We're going to talk about what are called factorization domains. This section actually has a few things that set it apart from other standard precalculus classes. You might not have ever heard of factorization domains, but they're important. They basically tell you what kind of numbers are allowed in a factorization. Then we're going to talk about a critical corollary that's related to the fundamental theorem of algebra. This is a bit of foreshadowing, a bit of looking ahead to section 3.5, but we're going to talk about it now just to give us some just meaningfulness for why we care about this stuff. We're going to go through some forms that you do need to memorize. Remember how I feel about memorization. Not a big fan of it. So when I say you need to memorize something, I mean it wholeheartedly. You are going to have to memorize these structures. We're going to talk about how to factor quadratic polynomials after that. And then we're going to get some deep motivation for why we even care about doing this. Just remember those important questions that I mentioned on day one. You should always be asking, why am I learning this? Why should I care about this? When am I going to use this in my STEM career? We're going to answer those questions right here when we get to this part. Then we're going to finish up by talking about difference functions and root finding problems. This is another thing that distinguishes this course from maybe a standard pre-calculus course, because we have an explicit discussion about root finding problems, which are just fundamental problems in math and science. So we'll get there in a few minutes. But let's start with reviewing factors versus terms. So remember that factors are parts of a product. And these are the same examples I gave back in section, oh geez, maybe 1.6, I think. Anyway, so like 12 is 3 times 4. Was it 1.6? Maybe it was 1.2 or 3. Anyway, um, 12 is equal to 3 times 4. So 3 and 4 are factors of 12. They're parts of a product, right? This expression, this is a quadratic polynomial that we can factor. We factor it into x plus 1 times x plus 2. So x plus 1 and x plus 2 are factors of this expression right here, okay? That's what we do when we factor something. That's a factor. All right, so what is a term? Terms are just expressions that are separated by plus and minus. That's what distinguishes terms from factors. So for example, this expression here has two terms, x squared plus 1, and the two terms are x squared and 1. The expression 5x to the eighth just has one term, 5x to the eighth. That's it. So the important thing here is that factors and terms are not the same thing. So be careful. They are not the same thing, and you can't treat them the same way. And being comfortable with that difference is going to be critical. In my experience, a lot of times when students make arithmetic errors when they're doing the algebra right, it's because they're mixing up terms and factors, and they think that terms and factors are like the same thing, and so they try to work on them the same way, but they're not. They're very different. And I'm going to give you an example in two slides here. So, oh yeah, just another note. This is from earlier as well. The number one is a factor of every number. Every number is divisible by one. Yeah, that's it. So here is the big idea for the whole section. Like, if you ever wanted to know, like, what was the deal behind factoring, it's this big idea. The process of factoring involves taking an expression with a lot of terms and rewriting it as an expression with one term, but possibly many factors. Okay? This is something that I want you to ponder for a sec. So think about it for a moment. Okay, and then I want you to read it out loud to yourself. Maybe try to say it in your own words. Remember, you don't have to say it to anybody. Just give your brain that feedback. Just say it out loud. Right. So that's the goal. The goal is we want to take an expression with a lot of terms and convert it into an expression with one term, but maybe that expression will have a lot of factors in it. Okay? Let's practice a bit. This is I love this question. I actually asked this question in all of my math classes because it just hammers home the difference between factors and terms. So here is my question to you all. How many factors appear in the following expressions as they are written? And then how many terms appear in these expressions as they're written? So don't manipulate them any further. Just look at them. And the question is, how many factors are there? And then how many terms are there in that whole expression? Okay. So stare at this one for a minute. Okay, and then better yet, say some stuff out loud. If you're watching this with your peers or with your colleagues, this is a great one to do together and talk to each other about. Ask them what they think. They should ask you what you think. Try it out. Okay. Then write it down. Write down. So basically, for like this question here, how many factors, how many terms? Just as it's written, just as it's written. No changing it, no manipulating it. Right. Okay, here we go. So, the reason this is an interesting question is because it will really hammer home the difference between factors and terms. So, in this expression here, there's one factor. There's one factor, and it's the entire expression. But there are three terms. One, two, three. So this expression has one factor, the whole thing, but three terms. Okay? Now let's move down to here for a second. As it's written, this expression has one term. It's got one term. It's right here. It's the whole thing. It's just that one term. But it's got two factors. This factor and this factor right there. Now you might be like, well, what about x and 1? Sure, those are terms of this sub expression. Those are terms in this factor, but those are not terms of the whole expression. The whole expression has one term, this big old thing right here. That's the one term. But it's got two factors. There it is. Okay, this one also has one factor, two terms. One factor, the whole thing, two terms. Okay, now the last three are basically what we do when we factor an expression. Okay, so this expression here, number four, it's got one factor as it's written, the whole thing. It's one factor, but it's got two terms. One, two. Those are the two terms. Now what we're going to do is we're going to factor this expression. And when we factor it, the first step, we're pulling out a factor of 3x, right? So this becomes that through the process of factoring. And now this new expression has one term, the whole thing, just one term, but it's got three factors. One, two, three. Three factors. So we took an expression with one factor and two terms and turned it into an expression with three factors and one term. You see there's like a difference there. But this is not, quote, fully factored. We could factor this expression even more over the integers, meaning using only integers, we could factor even more because we've got a difference of squares here. We're going to talk about those in a minute, but we can factor this as x minus 2 times x plus 2. So now we have one, two, three, four factors. So we took an expression here with two terms, one factor, and we converted it into an expression with one term and one, two, three, four factors. That is the process of factoring. All right, that's the idea. Here's the answers right here, by the way, just to have them listed. So when I was looking at this, I mentioned something about factoring over the integers, and that leads us to talking about what are called factorization domains. So when we factor quadratics or just polynomials in general, we have to specify what factorization domain we're factoring over. And what that means is the kind of constants or the kind of numbers that are permissible in a factorization. The standard factorization domains are the integers, the real numbers, and the complex numbers, which we'll learn in a couple sections. So what I'm really saying is When we say to factor an expression or factor a polynomial, we need to specify what domain we're factoring over. And what that means is what numbers are allowed in the factorization. Is it only integers? Or are we allowed to include real numbers because, or any real number? Because the real numbers include irrational numbers. Those are not integers, right? Or are we factoring over the complex numbers? Are we going all the way up and saying you can even include I and multiples of I and things like that, right? We have to specify that when we factor things. That's what the factorization domain is. Yeah, and that factorization domain determines whether a function, or sorry, whether a quadratic or just a polynomial is fully factored, right? Fully factored over what domain? The integers, the reals, the complexes. Let's see some examples. So let's factor over the integers for a minute. This expression right here, x squared minus 5, it's fully factored over the integers because there's no way you could split this expression up into more factors without, I'm sorry, by only using integers. There's no way to break this apart into factors where the factors only contain integers. However, it is not fully factored over the real numbers because if we're allowed to use real numbers, in particular, we're allowed to use irrational numbers, we can factor this further. We can factor it like so. Yeah, this might seem a little weird, but let me show you that these two things are indeed equal. Okay, I'm just going to distribute this. I'm going to redistribute it using the FOIL method. I'll use blue. So like x times x gives me x squared. X times root 5 gives me x times root 5. Negative root 5 times x gives me negative x times root 5. And then last, oop, there you go, sorry. Negative root 5 times root 5. Okay, well, check this out. These two terms cancel, and this last term here, negative root 5 times root 5, that's equal to 5. So this becomes x squared minus 5. There we go. So this is why the factorization domain is important. This is fully factored over the integers. It's not fully factored over the real numbers. If we are allowed to factor over the real numbers, we can factor it further, just like we did right here. Let me erase this. Yeah, we can factor it even further. Now it's fully factored. Can't factor this anymore. It's fully factored. Okay, let's look at another example. Here is an expression that is fully factored over the real numbers. So this one is, it's fully factored over the real numbers, and we can't factor it anymore if we're only allowed to use real numbers. But it is not fully factored over the complex numbers. We're going to see why in section 3.6, but you could factor this even further as x minus 3i times x plus 3i, where I is equal to the square root of negative 1. We'll talk about that later. It's not as weird as it might sound, but the point here is the factorization domain is important because if I say factor this over R, you're done. You don't need to do any more. You're done. But if I say factor it over C, you got to go one step further. You got to factor it even more to get that. Okay. So that's what the factorization domains are. Now, why do we care? Like, why do we need to know about factorization domains? Um, Mainly because of the fundamental theorem of algebra and this critical corollary to the fundamental theorem of algebra, this one right here. We will explore this again and restate it in section, I think, 3.7. Yeah, 3.7. And it's this. And this is just a really important thing to take to heart. Every polynomial can be fully factored over R into a product of linear or quadratic factors. Okay? And then furthermore, every polynomial can be fully factored over C into a product of linear factors. Okay? This is an astounding result. This is an incredibly powerful result to have. This is saying, and I'm going to let you think about this for a minute too. This is saying every polynomial can be factored. Every polynomial can be factored. Okay? So I want you to think about this for a minute. Just ponder what this says. Yeah. And now say it out loud. I want you to repeat this out loud to yourself, to your friend, to your dog. Just repeat it out loud so that it settles. Okay. All right. I need to re-emphasize this. So the reason that this is so important, and I kind of do this in my classes, every polynomial can be factored. So what I like to do in my classes is I will go in and I will just throw up a random polynomial on the board that's degree 5, right? With some crazy, like, x to the fifth minus 3x to the fourth plus blah, blah, blah. And I'll just ask the class, can this be factored? The answer should be an immediate yes. Yes, it can be factored. Why? The fundamental theorem of algebra. Yeah, this is what I always tell instructors too. I'm just like, you know what? If you're wondering if you've covered the fundamental theorem of algebra well enough, go into the class, throw up any polynomial, and just ask, can it be factored? Because the answer is yes. It's a hard yes. And here's the best part. If you're only allowed to factor over R, no matter how crazy that polynomial looks, your factors are going to be linear or quadratic. All right. If you allow yourself to use complex numbers, every factor will be linear. Every factor will be linear, meaning it'll look like, ax plus b. That's a linear factor. Okay. Quadratic factors look like ax squared plus bx plus c. So if you're only factoring over r, all of your factors of your polynomial will look like this or this. If you're factoring over c, all of them will look like this. Pretty amazing. Pretty amazing. We'll see why even more as we go along. Okay. Now, on that note, need to switch gears a tiny bit and give you some forms to memorize. I try to scaffold these a little bit as the course goes along. So these are the perfect square trinomials. Hopefully you've got these memorized already. We talked about them back in chapter 1, and the reason that we wanted to memorize them is because these are factorable. We can factor this as this, and we can factor this as this. So you want to train your brain to be able to recognize that you might be able to factor that type of a structure, okay? So these ones, hopefully, if you don't have them memorized, you've at least they're at least somewhat familiar. But if you don't have them memorized, please do make sure to memorize them. They're important. Now we're going to introduce another important form. This one is called a difference of squares. Let's look through the name for a minute. Difference of squares. There we go. Why is this such an important structure? Because it factors really, really nicely. A squared minus b squared factors as a minus b times a plus b. Boom, there it is. So that's what's called a difference of squares. You need to memorize this structure, commit it to memory, use flashcards, quiz each other in class, outside of class, just walk up to your group mate and be like, what is a squared minus b squared? Factor it. And they should be able to do it instantly, instantly. Okay? Now, kind of alongside differences of squares, we've got these. We have sums and differences of cubes. Let's walk through the names again just for a second here. Sum of cubes, a cubed plus b cubed. Okay. Then we have difference of cubes. That's why they're called that. And again, these structures are important because they have a beautiful factorization. And this factorization you have to memorize. Okay. You got to memorize it, right? So here is how the sum of cubes factors a plus b times a squared minus ab plus b squared. That's it. There it is. So a cubed plus b cubed, it factors. This is why that corollary is so important. Does this factor? Yes, it absolutely factors by the fundamental theorem of algebra. It factors into this. And if we're only using real numbers, this is as far as you can go. But if you're using complex numbers, you could actually factor this even further. We'll talk about that later, but we're not worried about that right now. We don't know much about complex numbers yet. But this is the structure. Notice the structure for the difference of cubes is very, very similar. A cubed minus b cubed factors as a minus b times a squared plus ab plus b squared. So what I want to point out is this. The structure of these two factorizations is very, very similar, right? A squared, ab, ab, b squared, b squared. So it's kind of like the size of the terms are the same, even like a, b, b. The only distinguishing characteristic between these two is the signs, right? This one's a plus, this one's a minus. This one's a minus, this one's a plus. So how do you memorize this? Because this is exactly the kind of thing that I would mess up. Like I would mess up because I don't know what the signs are going to be. I could probably remember a, b, and a squared, ab, b squared, but I wouldn't know about the signs. Well, one of my students taught me this really handy mnemonic many, many years ago, and he said, "Oh, I remember it by using SOAP." And SOAP stands for same, opposite, oops, opposite, and then always positive. And he said this will tell you what the sign of the terms should be. So it's easy to remember a, b, a squared, a, b, b squared, but what are the signs? So the sign here will be the same as the given sign. This one will be the opposite of the given sign. And this one is always positive, always positive. There it is. So, and it works for both. It works for both, not just the sum. It works for the difference, right? Same, opposite, always positive. Soap. There you go. All right. So these are the forms that you need to have memorized. They're right here on this slide, summarized right here. These are all the structures. These are just special factor forms. This will help you factor perfect square trinomials. This will help you factor a difference of squares, and this will help you factor differences and sums of cubes. All right, there you go. So memorize these, commit these to memory. The other important thing about these particular forms is that these are structural, and this is where the math gets really fun. They're structural, so it doesn't really matter what A and B are here. A and B can be any expression. They don't have to be numbers. They don't have to be letters, like individual letters. They can be any expression. So you can have A and B be any kind of crazy mathematical expression you can imagine. If you have this structure, crazy thing squared plus 2 times crazy thing plus crazy thing squared, you can factor it. And you can factor it as this. It's a structural similarity or a structural equivalence. Okay. Um, Another little side note down here, when you are factoring over R, there is no sum of squares formula. Sorry. Yeah, when you're factoring over the real numbers, there's no sum of squares. A squared plus B squared is as factored as it gets over the real numbers. I mean, unless B and A share common factors, and then you can factor them out and so on. But there's no formula for the sum of two squares that's valid over the real numbers. However, there is one when you factor over C, when you factor over the complex numbers. And we're going to see that when we get to section 3.6. All right. Okay. Now let's practice this a bit. So these are some examples. I want you to try them at home. And we're going to do a lot of these types of questions in the activity as well, just to get those juices flowing and get you comfortable with factoring these types of things. So we'll start with just these two. And I want you to, oops, where is it? Think about it for a second. Look at the structures. You can use any technique you want to factor. Okay, now say something out loud to yourself, and then try to work out these two, and we'll do it together in just a second. Okay, now let's do it together. This one is the form of a perfect square trinomial, so it factors. This is x squared plus 2 times 5x plus 25, x plus 5 squared. Done. This one also has the form of a perfect square trinomial, but you might have to be a little bit clever. You might have to recognize 9x squared as 3x squared, but then 6x is 2 times 3x and or times 3x times 1, and 1 is equal to 1 squared. Maybe I should have put a squared right there. right? Pretend there's a squared right there. There you go. So it factors as 3x plus 1 squared. Okay, next batch. Try to do these ones. Remember, these are all about special forms. So see if you can recognize the form and work it out on your own. Right? Now let's do it together. This type of structure is something you want to be able to recognize instantly. So start training your brain now. These are both differences of squares. Those are both differences of squares. This is x squared minus 1 squared. This is 5x squared minus 2 squared. So they factor immediately by the difference of squares formula. X minus 1 times x plus 1. This one is 5x minus 2 times 5x plus 2, just like that. All right, difference of squares. Okay, one more batch. Try to do these two. Think about them, talk to yourself or talk to your friend about what they look like, and then try to factor it on your own. Okay. Now, these two both have structures related to cubes. This one is a difference of cubes, and this one is a sum of cubes. You just might have to massage things a little bit to get the cube structure to show up. This one is x cubed minus 3 cubed. Remember, we had that question on the homework about just writing down the first, I think it was like 5 cubes, perfect cubes. This is why, because you want to be able to recognize 27 as a perfect cube. And then this one, you can think of it as 2x cubed plus 4 cubed. That's a sum of cubes. More specifically, we have this. Here's the cube structure, and then here's me using the formula, just plugging it in. A squared plus AB plus B squared. Remember the signs, right? Same, opposite, always positive. Same, opposite, always positive. And then I just simplified a little bit at the end. There we go. Now, same thing for the next part. This is 2x cubed plus 4 cubed. Use the sum of cubes formula. A, B, A squared, A, B, B squared. Signs, right? Same, opposite, always positive. And then just simplify a little bit. 2x squared is 4x squared. 2x times 4 is 8x, and 4 squared is 16. There we go. And also, I'll say these. This is factored. You can always factor a little bit more. Like you could have factored out, I shouldn't say always. A lot of times you can factor a little bit more. Kind of just depends on what you're going for. You could factor out a 2 from this still. Let me just show you. Actually, you could factor out even more. Now that I'm seeing this, let me do a secondary example here. One thing we could do is this. Notice that both of these terms, they have a common factor of 8. So we could factor out an 8, and then we get this other version. So this is, well, I'll just write it like this. 8 times x cubed plus 8. There we go. Now we can use the sum of cubes formula again. So this is going to be 8 times x plus 2, x squared, same, opposite, times AB. So that will be 2x plus 2 squared, which is 4. There we go. Yep. And these are both equal. So that's like a full factorization right there. I could factor this even more. All right. Okay, so now we've talked about those special forms. Next thing we got to talk about are quadratic polynomials and then factoring quadratic polynomials because a quadratic polynomial is a more general structure, right? A quadratic polynomial is an expression of this form here. Any expression of that form where x is our variable, a, b, and c are constants, and a is not 0. If a is 0, then this term disappears and you don't have a quadratic anymore. You've just got like a linear expression at that point. So the thing is that not every quadratic polynomial is a perfect square trinomial or a difference of squares or a sum of squares, or like, they don't all have that structure. This is a very general structure. So the question is, how do we factor that? If we can factor it further, right? So here are the steps. So here's how you can factor a quadratic polynomial. First thing is factor out the greatest common factor from all terms. I'd actually done that here on this example, even though this is not quadratic, right? But I factored out the greatest common factor first. Then you can use one of the forms above, right? You could use one of the factor forms if we're lucky, or you can factor by grouping, which I'm going to show you how to do now, or you can use guess and check. So when I first learned this stuff way back in high school, they didn't teach us any of this. They just did guess and check. And we had to basically practice factoring, geez, hundreds and hundreds of times in my math class, which is why I really hated factoring back then. So, well, I'll say this. I really hated it, but over the many years that I've been doing math, I've gotten a lot better at guess and check, but it's nice to know that it can always use factoring by grouping. Factoring by grouping is a little more procedural. It's a little more algorithmic, and so I'm going to show you how to do it here. But I want to say this here. I don't have it written down, but you can use whatever factoring technique you are comfortable with in this class. You don't have to do it this way. There will be a couple times on the homework where I ask you to do it this way, just for your own edification and your own practice. But when it comes to things like the test, or it comes to, any application in your actual life or your career, just use whatever factoring method you know how to do that you're comfortable with. Okay? Okay, just wanted to say that. So let's talk about how to factor by grouping. Let's learn at least one process that you can always use. So here's how you do it. If you've got a quadratic expression of this form, you can factor it by grouping using this four-step process. One, compute A times C. A is the leading coefficient. C is this constant term. You're going to multiply those two values together to get some number. Then what you have to do is you have to find two numbers, B1 and B2, whose product is A times C, but also whose sum is equal to B. All right, so you're multiplying A and C, and you got to find two other numbers that multiply to give you AC and add to give you B. All right, that's the second step. Then what you're going to do is you're going to rewrite the polynomial using these two numbers B1 and B2. You're going to split up BX as B1x plus B2x, whatever those B1, B2 numbers are, okay? All you're doing is rewriting this term in this form. It's a structural change. And then you're going to factor by grouping. What you're going to do is you're going to group this pair and you're going to group this pair and just factor out single factors, factor out single common factors, and then you're going to factor again. That's the factoring by grouping. I'll show you how to do it right now. Okay, factor this completely. We're going to use factoring by grouping. Again, you could use guess and check. Just recognize that you're going to write it in the form that, and then just figure out what's going to go here and what's going to go here. Guess and check. You could just do guess and check, and it may not take you that long. You might get lucky and get it right the first try. But assuming that you don't want to do that, let's factor by grouping. First, we multiply 2 and 3 to get 6. Now what we need are two numbers whose product is 6, but whose sum is 5. In this case, it happens to be 2 and 3, right? 2 times 3 is 6. 2 plus 3 is 5. That's it, okay? Just coincidence that they happen to be these same numbers, just a coincidence, all right? But these two numbers add up to 5 and they multiply to be equal to 6. Now we're going to rewrite 5x as 2x plus 3x. Okay, that's all we're doing. We haven't changed anything. This is taking this middle factor, I'm sorry, this middle term, and splitting it into two terms that we've chosen cleverly. Now we're going to factor by grouping. So here we go. We're going to take, we're going to take these two terms and factor as much as we can out of them. So there's a common factor of 2, and there's a common factor of x. So we're going to factor 2x out of both. And then we're left with x plus 1. Now we're going to do the same thing to this pair. And we're going to factor as much as we possibly can out. So here we're going to factor out a 3. Oops. We can factor out a 3 from both of those terms, and it looks like that's it. So 3 comes out, 3 comes out. We get 3 times the rest. Okay, now here's the cool part. If you look at what remains, each one of these terms, see, there's only 2 terms now. There's this term and this term. There's 2 terms in the whole expression, but each of those 2 terms has a common factor of x plus 1. So we're going to factor that out. We're going to factor out x plus 1, and then we get x plus 1 times what's left over, 2x plus 3. 2x plus 3. One thing I like to show, oh, wait, by the way, this is now fully factored, so we're done. That's fully factored. What I like to do is I kind of like to show in reverse how this step works, because this can be kind of confusing where you're like, wait, what, like, how did he do that? How did he go from there to there? Um, all you got to remember is the difference between terms and factors, okay? So I'm actually going to reverse the process. I'm going to take x plus 1. Actually, let me erase some stuff. Getting a little bit cluttered here. Um, I'm going to take x plus 1 here, and I'm going to distribute that whole factor to these 2 terms. So x plus 1 times 2x, x plus 1 times 3. And when I do that, I'm going to get 2x times x plus 1, sorry, plus 3 times x plus 1. And look, that's the same thing. So this is why the difference between factors and terms is so critical, because I'm taking this as a whole expression, or like it's one factor, right? This is one factor. And I'm going to take that single factor and distribute it to these 2 terms, So it's this whole thing getting distributed to each one of those pieces. And when I do that, I get this. Now, if I wanted, I could continue. If I continued to expand this, I would end up getting this again. So maybe I'll do one more step, and then you can do this the next step if you really want. This will become, oops, erase. There we go. So I'm going to take 2x and distribute it to x and the 1. That'll give me 2x squared plus 2x. I'm going to take the 3 and distribute it to the x and to the 1. I'm going to get 3x plus 3. Notice this is identical to this. And now I can combine like terms. I can combine 2x plus 3x to get 5x, and now I've got that again. All right. So factoring is like reverse distributing. Factoring means we're starting with a bunch of terms, and we're ending with one term, but 2 factors or more, depends, right? One factor, 3 terms, one term, 2 factors. And that's the process of factoring, all right? Okay, now let's take it up a notch real quick. Try to factor this expression completely, okay? And here's one. I'll say this. I want you to at least think about it on your own. If you don't want to try it on your own, that's fine, but think about it. Think about factoring that completely and see if you notice anything special about the structure of this expression. Okay, now say something out loud. Do you notice anything common about some of the terms in this expression? All right. Now, if you want to try to do it yourself, go for it. But I've got one requirement. You are not allowed to multiply everything out first. Okay? You got to factor it the way it is. The one thing you're allowed to do is you could make a substitution, and then we're going to do it together in a moment. Okay. Here we go. All right. So here's the cool thing. This is a quadratic expression, but it's quadratic in a different variable. Let me explain what I mean. So each one of these first two terms has a common factor of x plus 2, right? So we could actually view this polynomial, quadratic polynomial, as quadratic in the variable x plus 2. This is like blah squared plus 11 times blah minus 12. That's quadratic in structure. Blah squared plus 11 blah minus 12. That's quadratic, right? So when that happens, when we see a structure like this where uh, the expression is quadratic, well, just in a different variable, we just say it's quadratic in whatever that other variable is. So, or whatever that expression is. So this is quadratic in x plus 2. Now, you don't have to do this step, but sometimes it helps to relabel. We could rewrite x plus 2 as y. So then this is y squared, this is y. And so our whole expression becomes this. Now, maybe when your brain processes this, you're like, "Oh, I see it now." Great. That's the purpose of the relabeling here. So if you really, really need that, then just replace these with y. Just remember at the end that your original polynomial was in terms of x, so you're going to have to resubstitute at the end of all that process, okay? So now factor it. You can factor this. You can factor by grouping, factor by guess and check. Just remember you need two numbers that multiply to be this and add to be this. I think 12 and negative 1 will work. There we go. 12 and negative 1. Can always check. Y squared minus y plus 12y. That's 11y minus 12. Boom. There you go. Now it's factored. Now we're going to resubstitute. So we can change y into x plus 2 again. And then simplify. X plus 2 plus 12. X plus 2 minus 1. And there it is. Okay, so this thing factors as this. That's what it looks like when it's factored completely. All right. Um, Now, I do have this note. So we could have arrived at the same result if we had just multiplied everything out in the beginning, right? If we could have expanded this and then combined like terms, we would get something that factored into this. You could do that, but a lot of times that technique can be more difficult, or it may not even be possible because there's no rule that says this is always going to be two terms that you can square. And like, I mean, this is not going to be a binomial where you can multiply it by itself and factor it out, or I'm sorry, distribute everything. That's not always going to happen. What's important here is the structure is quadratic, because this can be anything. That could be anything. And we're going to see that more in chapter 4 and 5 and 6. So it's good to get comfortable with it now. And we'll reiterate it and reinforce it as we go on. Okay, so this is a lot of work, right? Hopefully by now you're feeling kind of the same where you're just like, man, this is a lot of work. Why do I care? Like you should ask these questions. You should ask these questions. You deserve answers to these questions. Why do we even care about this? Why go through the pain of learning this and figuring it out and practicing it maybe hundreds of times, learning these techniques, guess and check, factoring by grouping? What is the point? What is the point of all this? This, this. And this is what we're going to learn over the next couple sections. One, remember what factoring does. This was the big idea at the beginning of the section. Factoring lets us convert multiple terms into a single term with multiple factors. Okay? Now, this idea extends to polynomials in general. Right now, we've only talked about factoring quadratics, but as we go along in this chapter, we're going to factor polynomials in general, okay? So this whole idea of factoring extends to polynomials. Now, that combined with this, the fundamental theorem of algebra says that every polynomial can be factored. So we're learning how to factor quadratics because we're going to be factoring polynomials in a section or two. The fundamental theorem of algebra says you can always factor a polynomial until you get linear or quadratic factors. Okay, great. Now, there are these things called root finding problems, and that's what we're going to finish the section with, root finding problems. Root finding problems are just problems that involve finding the zeros or the roots of continuous functions. Okay, we talked about finding zeros of functions in the previous chapter. Well, I also briefly mentioned root finding problems. This turns out to be a critical technique in STEM, not just Calc 1, not just Calc 2, not just Calc 3, not just math, but STEM in general, okay, science. Then, then we have the zero product property. The zero product property is what establishes a relationship between factors and zeros or roots, okay? Then we have this theorem, which you probably never heard of before, but now you will, and we're going to talk about it at length in section 3.5, the Stone-Weierstrass Approximation Theorem. And this approximation theorem yields a polynomial approximation of any continuous function on a closed interval. Okay, so why do we care about factoring? Here's the big picture. For one, Fundamental Theorem of Algebra says every polynomial can be factored into factors, right? Zero product property establishes a relationship between factors and zeros. Root finding problems are common in science. We basically come up with a problem that we can describe in terms of finding the zeros of a function. The Weierstrass Approximation Theorem says, hey, as long as your function is continuous on a closed interval, we can find a polynomial that approximates it as close as you want. So here's the big picture. Pretend you're working with some gross, nasty function in whatever STEM application you've got. Weierstrass Approximation Theorem says, hey, we got a polynomial for you that'll work as long as you're allowed a little bit of error. Remember the theory of approximation. If you allow us a tiny bit of error, you could just use a polynomial instead. Oh, great, I'll use the polynomial. Now, guess what? Every polynomial can be factored. Guess what? Once you factor the polynomial, there's a relationship between the factors and the zeros. So that root finding problem that you're struggling with that nasty function, we just found a way to solve it as long as you admit a little bit of error. The good news is the error can be as small as you want. We control that. That is why we care about factoring. Okay? We'll talk more about that as the course goes on. I can tell you more in class, but let's quickly review the zero product property and then let's talk about root finding problems. Let's get you set up for that skill. So here's the zero product property. You've probably heard of it before. It's critical. It basically says this: if a product A times B equals zero, then either A is zero or B is zero or both are zero. That's the zero product property. In other words, if a product is zero, then any of the factors could be zero. I'm sorry. There must be at least one factor that is equal to zero, or they could all be zero, right? That's the whole idea. Either A is zero, B is zero, or they're both equal to zero. Just more generally, this applies to products, okay? So for example, if you know 5x equals zero, that means x has to be zero by the zero product property. This is why factoring is nice because, well, I think I say it here. Wait, do I say it here? Yes. I guess I don't quite say it there, but the idea is this. If you have an expression that has a bunch of terms in it, added and subtracted, and they're all that sum is equal to zero, it's actually really hard to solve. But if you can factor it, it makes it much easier to solve. So let's talk about root finding problems. And to talk about root finding problems, they often come paired with what are called difference functions. That's what we're going to set up right now. Um, this is one of those techniques, one of those concepts that, again, sets this course apart from a standard precalculus class. We need to have an explicit conversation and an explicit exploration of this concept because you will use it over and over and over in your STEM career, okay? So suppose your exploration has allowed you to construct two functions, f and g, and led you to the point where you need to solve this equation. You need to know where the first function is equal to the second function in terms of the outputs, right? When does the output of f equal the output of g? So It turns out that in practice, more often than not, it is quite difficult to solve an equation of this form for the input x. So to make things easier, we rewrite this equation as a difference equation. Okay, so all I did was I subtracted g from both sides, g of x, and now I get f of x minus g of x equals 0. This is what we call a difference equation, and we want to solve this difference equation for x. Okay, we're setting things up. We want to find the zeros of this difference function. And you know what? It's actually easier to refer to this difference as its own function, the difference function. So we can reframe things. Instead of thinking about it as f of x minus g of x, we can define a new function, call it d, and we're going to call d the difference between f and g. So d of x is f of x minus g of x. So d of x is the difference function. And what we've now got is a single function. And if we want to know the solutions to this equation, we just need to find the zeros of this function. Well, haha, see, now everything's coming together. This is why we talked about zeros of functions. Everything's coming together. We've re-expressed our problem as a root finding problem. Wait, do I say that next? Oh, yeah, that's what I say on this slide. We've now re-expressed our problem as a root finding problem. We just need to find the zeros of this function d, whatever that function is. And now we're opening our world is opened up with all these different techniques, right? If we can find the zeros of this function, then that means we have found where f of x equals g of x. So this whole process is just a reframing of the original problem in a structure that is more easy to solve, like easier to solve, easier to approach. Okay. Now, here is the best part. If d of x is a polynomial, then it can be factored, and the zero product property can be leveraged to find the roots of this equation, right? If d of x is a polynomial, we can factor it. If we can factor it, then we can find all of its zeros because there's a correspondence between the factors and the zeros by the zero product property. Okay, what if our function is really gross? What if our function is not a polynomial? The Weierstrass Approximation Theorem. The Weierstrass Approximation Theorem says, hey, we can give you a polynomial that is as close to whatever function you're working with as you like, as long as you remember there's a tiny bit of error. All right? That's the big picture, okay? That's the big picture here. So the other cool thing is this difference function that we've set up and defined, it also describes the order relationship between these outputs, f of x and f of g, right? It describes the order. It tells you which one is above and which one is below. And when they're equal, they're at the same level. So if this difference function is negative, if I'm sorry, if d of x is negative, the output, that means f of x is below g of x. Think about it in terms of a graph we're going to see in a moment here. If d of x is negative, then the graph of f is below the graph of g. If d of x is equal, the graphs intersect. They're touching, they're at that same level. If d of x is positive, then the graph of f is above the graph of g. And even better, the absolute value of d of x is the size of the difference. It's literally the distance between those two values, the distance between the two graphs of those functions. So by characterizing everything in terms of this difference function, the analysis of the problem becomes easier. Okay, that's the big idea. And now let's use it. Let's try it. Here we go. We're going to do a simple example. I want you to try it first and we'll do it together, but I want you to find the points where the graphs of the functions f of x equals this and g of x equals this intersect. And I want you to find the intervals where the graph of f is below the graph of g, or vice versa. Where is f above g? Where is f below g? And where does f equal g? Okay? All right, now think about it for a second. Just like kind of sit back, let it wash over you, look at what's written here. Now say something out loud about what you're going to do first. Okay. And now work on it on your own. The one stipulation I will give you is this: use a difference function. Set up a difference function first. So set up the difference function, find the zeros of the difference function, and then that will help you determine where the two graphs intersect and where one is above the other or below the other. All right, you try it for a second, and then we'll do it together. Right, here we go. Okay, so let's define the difference function first. We're going to call it f of x minus g of x. We're going to plug in the formula for f, plug in the formula for g. Remember, parentheses are your friends. Parentheses are your friends, okay? Now we're going to simplify. So our difference function is given by this polynomial here. So finding the zeros of d of x is equivalent to finding the x values where the curves intersect. That's all we need to do. So we're lucky in this case that we actually have a polynomial. We have a quadratic polynomial. So what we're really doing is we're finding the zeros of this quadratic polynomial. This quadratic polynomial factors over the integers. It factors as x plus 4 times x minus 1. So by the zero product property or zero product principle, this tells us that x has to be negative 4 or x has to be 1. Boom. So we know that the graphs intersect when x is negative 4 or x is 1. That's where the two graphs are going to cross in some way. All right. Now the question is this. When is the graph of f below or above g? Let's figure that out. Well, because we know these zeros, we already know where the graphs intersect. We know where those values are equal. And so what we can do is, oh, sorry, I didn't finish the intersection part. If we want to know the actual points where the graphs intersect, we can take the input values we just got and plug them into either function to get the y values. Sorry, jumping ahead on that one. So plug in negative 4 to g or f. G is easier. And then simplify. So we get negative 7. Plug in 1 to g. We get 3. So we have 2 points of intersection. Negative 4, negative 7, and 1, comma 3. That's where the two graphs intersect. Now we can find the intervals where f is above g or vice versa. Here we go. Now, remember, d of x gives us the order relationship between f and g, f of x and g of x. We found the zeros, so that is where f of x equals g of x. So now what we're going to do is we're going to create what's called a sign diagram and do what's called a sign analysis to figure out where the graph is above or below. So what you do is you make a you make a number line. This number line represents d of x. Here we're plotting the zeros first. So those are the two zeros of d of x, right? Negative 4 and 1. And then we're just going to test values in between these 2 points. On all sides of these 2 points, I should say. And when I say test values, I mean test in d of x. So pick any point you want to the left of negative 4 and plug it into d of x. I picked negative 5. D of negative 5, I plug it in, and I get a positive number. Yeah, positive number. So that means that this has to be true. So that means f is above g on that interval, f of x. Now pick any point in between negative 4 and 1, and go for the lowest hanging fruit. Pick the easiest point you could imagine, 0. Let's plug 0 into d. We get that, get that. This is a positive times negative. That's negative, so it's below. The graph of f is below the graph of g there. Now pick any point greater than 1. How about 3? So we pick 3, we plug it into D. Oh, wait, does that say 3? I did 2, my bad. So I'll fix that. That should say 2. I take 2, I plug it into D. I get positive times a positive, which is a positive. So F is above G on that interval. Um, yes, okay. So let me do this. Yeah, actually, before I do that, let me make a note here. One thing I want to point out about these calculations down here is all we care about is the sign. We don't really care about the exact value of the calculation. We just need to know if it's positive or negative. That's why I didn't actually compute this. But this will be negative, this will be negative. Negative times a negative is a positive. Positive, negative, positive times negative is negative. Positive, positive, positive times positive is positive. That's all we care about, the order relationship, right? Now that we have those values, remember this should be a 2. There we go. Now that we have those values, we can see that the graph of f is above the graph of g on these two intervals right here. And the graph of f is below the graph of g on this interval right here in the middle. That's it. So these are just sample points, right? We're just taking sample points to get a sign to know the order of the two graphs. Now let's look at the picture itself. And the picture, I think, will hammer it home. We could sketch both of these graphs. We're going to learn how to sketch quadratic functions in the next section. We already know how to graph lines. That's what we talked about in the last section. And this picture kind of shows what everything looks like. So I'm going to zoom in. Let me go to these so I can zoom in a little bit more. Come on. Just a tiny bit more. There we go. All right, so blue, this is the graph of f. Red, oop, that's the graph of g. And what we found was, remember on this interval, so basically everywhere from -4 this way, the graph of f was above the graph of g. And that's exactly what we're seeing. And that's because the difference function is positive, right? The difference is positive. So the difference between these two values is positive on that interval. So that means f is above g, just like that. Then we had the same result way over here. The difference between these values is positive. So that means f is above g, right? D of x is positive, so the parabola is above the line. Then right here in the middle, we have the reverse, right? In between -4 and 1, we had that d of x was negative. The difference function was negative. This difference is negative, just like that, right? That's why the difference functions are so important, okay? Because we took this question of finding where these two graphs intersect and finding where one is above and below the other, and we converted it into a root finding problem, and then we did a sign analysis. So that's it, all right? That is a root finding problem, and that is how we're going to do it. And this is something that you're going to see when you get into Calc 1 and beyond. It's a technique that you just see over and over and over again. If you can convert your problem into a root finding problem, then you're set, you're golden, all right? All right, on that note, that's it. Let's play. This activity is going to be fun. I hope we can help you learn how to factor a little bit better. I hope we can talk more about root finding problems and maybe pique your interest more about the Weierstrass Approximation Theorem. Thank you all again for listening. I'll end the lecture here, and I will see you next time where we talk about the graph of a quadratic function, if I remember right. All right. Thank you again, everybody. See you next time.